Bismillahirrahmanirrahim. Assalamu alaikum. This is the 40th lecture of Formal Methods for Software Engineering, and I am Fakhr Lodi with you. We are discussing Z specifications. And today we shall start to discuss an application or a specification, concrete specification of an operating system component using Z. And then we will be applying some refinement steps to have, relatively speaking, a concrete implementation of that operating system component. The operating system component that we are going to talk about is a very famous, the scheduler. What is a scheduler? Scheduler is a component that takes a task from the ready queue and assigns the CPU to that task. So it performs certain operations, a number of operations, and we will be talking about those things, and there are a number of things that we need to take care of. In this example that we are going to discuss, we are going to have a number of constraints. That is, first of all, we are saying that there is only one processor available. So it is not a multi-processor kind of a thing, one processor. And we are going to use this scheduler to schedule tasks on that single processor. The other thing that we are going to use is that we are going to have a process which is using the processor. That process will be called the current process, and then we will have processes in our ready queue. Those are the processes that are there to be scheduled. They are waiting to be scheduled. Then we will have processes which are waiting for some other event, for example, an I/O, and those processes would be put in a queue called blocked. So a process which is a current process which needs an I/O would be put into the blocked queue. So we take this process from the ready queue, we put it in on the processor. It stays there for some time, and there is a time slot that is allocated. After that, it is timed out and it is put back at the end of the ready queue. And during processing, if it needs I/O, it is taken out of the processor and it is put into the blocked queue. So this is our basic kind of famous cycle of processes. This is what the processes they go through. That is, they come into the ready queue, they take the processor, they go after the timeout, they go back into the ready queue, or if they need I/O, they go into the I/O queue. Once they get that service, they are put back into the ready queue, and then they will get the process according to their own turn. The ready queue could be implemented by a simple FIFO, or it could be a priority queue, depending upon what scheduling policy do we want to have. But that will come later. So this is the basic kind of information about the scheduler. I think you are all familiar with operating systems, so there is no need to elaborate it any further. Now let us look at the specification. Start the specification and look at some of the other constraints, some of the things, some definitions that we need to have, and then we will have our specification. Our system will deal with up to n processes, where n is a natural number. Each process will be associated with a process identifier or PID. So this PID is equal to 1 to n, because we can have up to n processes. Then we have a special process ID called null PID, which is equal to 0. Remember, a proper process ID is a number which is greater than 0. And all the process IDs, they would be our PIDs and our null ID, that is the option of PIDs that we have. That is all the PIDs union this null PID. So this is the starting point. Let us now define the abstract state. We have this abstract state of a scheduler. We have this current, which is of type opt PID. We have this ready, which is a set of PIDs. We have blocked, which once again is a set of PIDs. And we have free, which is once again a set of PIDs. There are 4 variables we have defined here. One is the current. Current one means the one that possesses the CPU, the processor. And this is taken from all the process IDs plus the null process ID. That means it is possible that the CPU is not given to any process. There is no other process except for the processes of the operating system. So the CPU, the process on the CPU is, there is no process that has the CPU. So we need to have a null PID that means that currently no process possesses the CPU. It is quite possible that at some point in time we have that kind of situation. Except for the kernel, there is nothing there. Then we have the other processes. We have actually 4 partitions. Current, a single process or nothing there. Then we have a free PIDs, list of those PIDs which have not been taken. So remember that we said that we will have a maximum of up to n PIDs, n processes. So when a process comes, we assign a number from our empty free list, our free list. So if the free list has available PID, that available PID, one of those would be assigned. Which one? At this point in time, we don't know, and we are not talking about that yet. Then some of the processes will be in the ready queue. Some of the processes will be in the blocked queue or the waiting queue. So all the PIDs, whether they are assigned or not assigned, they have been taken care of. The PIDs that have been taken, that have been assigned, there are 3 possible places that we can find those PIDs. Either current, or in the ready queue, or in the waiting blocked queue. And in the free list, we have all the PIDs which have not been assigned yet. Now we look at the predicates. This current minus the null PID, this is 1. Then we have ready, then we have blocked, and then we have free. And these 4, they define a partition of the PIDs. I have already mentioned this thing, that we say that all the PIDs, they are taken care of here, and it is a partition. That means these 4 sets, they are mutually exclusive. The current has only 1, ready, blocked, and then the free list. So all PIDs, they will be found in this partition. Then we have the initialization part. So this is a scheduler init. It gives us a new state of the scheduler. So when we initialize, current gets this null PID, ready list is empty, blocked is empty, and free has all the PIDs. So at the time of initialization, there is nothing on the processor, on the CPU. There is nothing in the ready queue. There is nothing in the blocked queue. All these lists, all these sets, they are empty, and all the PIDs, they are present in the free PID list in that set. That is, there is no real process in the system at this moment. We have just initialized it. We have the following operations. Create a process which adds a process to the set of ready processes. Dispatch, which takes one of the ready processes and puts it onto the processor. Timeout, which takes the processor running on the CPU, that is the current process, removes it from the processor and returns it to the set of ready processes. Block, which removes the current process from the processor and adds it to the set of blocked processes. Wake up, which takes a blocked process and moves it into the set of ready processes. And destroy, which terminates a process. So these operations are the typical operations that a scheduler would perform. Creating a process, that means, adding a process to the ready list. Dispatch, taking a process from the ready list and putting it onto the CPU, assigning the CPU to it. Timeout, now when this time slice runs out, it takes it from the CPU and puts it back onto the ready queue. Then it takes this process and puts it into the blocking queue if it needs an IO. Wake up, that means IO has been completed. Now put this process back into the ready queue, and finally terminate a process. That means in that particular case, the process doesn't need the CPU anymore. It has completed its work, and hence it needs to be terminated. We are now going to specify all these different operations. The first operation is create. So we have this a create, which is delta a scheduler. It changes the scheduler. We have the output as a PID. P is a PID. The precondition is that the free is not empty. So we can assign a PID to this new process that is coming. This new current is equal to current. That is, we are not changing the state of the current. If there is a process which has the CPU, it will remain there. The ready now has this new process that has just come, which will be assigned a new PID. Blocked remains the same, doesn't change. Free has this P taken out of the free list, free set, and the new free is this old free minus this element P that is assigned, and this P that has been assigned should be a member of the free set. So in this particular case, what is happening is that when we need to create a new process and we need to put it in the ready queue, the first thing that we need to do is we need to assign a PID to this process. So first thing that we need to do is we need to check whether we have an available PID in our free set. So if there is no PID available, that means we cannot have any new process. We have all the n processes that have already been assigned, so we cannot have a new one. So this is the precondition. Then the rest is very, very simple. The only thing that we do is we take one element from the free set, that is the PID that we assign to this new process, and then that new process is put into the ready queue. So the ready set of the ready processes changes, as well as the set that contains the free IDs, that also changes. The rest remains the same. Nothing else changes. Current is what current was. The waiting set has the same set of elements that it had previously, and so on and so forth. So the two sets that they change is the ready and the free. The rest remains the same. Now we look at the specification for the dispatcher. What does dispatch do? Dispatch takes one element from the ready set and assigns CPU to that. So it changes the current. So let us look at it. So a dispatch changes the scheduler. It is a PID is the output, that is the process ID. Current is null PID, that is there is nothing on the CPU. Ready is not empty, there is something that can be scheduled. A new current is a member of the ready, that is we take one element from the ready and that will be assigned to this current, and that is what we get. The ready is now modified. We take this current which has been taken from the ready, so that has been taken out. So the new ready set is equal to the old ready set minus this element current. Blocked does not change, it stays the same. Free does not change, it stays the same. And the output is that the element current which has been dispatched. So once again, you look at this specification, there is nothing difficult about that specification. All it is saying is take one from the ready set. The condition must be that currently no process possesses the CPU and the ready set is not empty. If the ready set is empty, that means you cannot schedule anything. It cannot be put. You cannot take anything. So ready set is not empty, and the current state of the processor is that it is not occupied. If that happens, if these are the two conditions, only then this dispatch can be used. And what we do in that particular case is we take one element from the ready, and that becomes the current element. So we change the values of the current from null to this new value that has been taken from the ready set, and ready set changes, one element has been taken out, so we have a new set from which that element has been removed, and what we get is the remaining. The other, that is the blocked and the free, those two sets, they do not change because they have nothing to do with this dispatch operation. So these two specifications, that is the initialization and dispatch, they were straightforward specifications. But as you can see, there is a degree of non-determinism here. We are not saying which particular PID and which element from the ready queue or ready set and so on and so forth. So as far as this dispatcher is concerned and the initialization is concerned, when we add, it could add, could assign any PID to this new process that we are adding, and when we are dispatching, it could take any element from the ready set and give it the CPU. So we are not imposing any condition here. Let us look at the rest of the specification. Now we have the schema for timeout. Once again, it changes the scheduler, and the output is a PID. Current is not equal to null PID, that is, CPU has been occupied, some process has it. The new state of current, when this process times out, the new state will be null PID. Ready queue, ready set gets this new element that occupied the CPU. So it has been appended. It takes one more element. Blocked does not change, free does not change, and the output is current. So in this particular case, once again, you see the specification is straightforward. There is nothing special about it. We have seen the previous two specifications. This one is very much in line with those specifications. All we are saying is that in this particular case, when it times out, we set this current to be equal to null, and then takes this current and put it into the ready queue, and that's about it. The rest does not change. Now let us look at the remaining couple of specifications. A block which is similar, in this particular case it changes the scheduler. Current is equal to null PID. Now current becomes null PID. Ready remains ready, doesn't change. Now we take this current and put it into the blocked set, and so blocked set has one more entry. Free doesn't change, and the output is current, the PID. So this block specification, the specification for block is very, very similar to the timeout specification. The only difference in this particular case is that we, instead of putting this current process into the ready queue, which was the case in the previous specification, we put this process into the blocked queue. Nothing else changes. The rest is very, very similar. Now let us look at the rest. Now we have the specification for wake up. It changes the scheduler. Once again, the input is the PID. So this time we say we need to wake up this particular process with this particular PID. The first precondition here is requirement that this input is a member of the blocked set. That is, the process that needs to be taken from the blocked queue and put into the ready queue, blocked set, and put into the ready set has to be present in the blocked set. Current does not change. Now since we take one from the blocked set and put it into the ready set, we change these sets accordingly. So we take this element from the blocked set. So the new value of blocked will be the old value, the old set minus this element P, and the ready will be updated. And in this case, the new value of this ready set will be equal to the old ready set union this element P. And free does not change. Once again, nothing very special here. Almost the same formulation that we have seen in so many different cases. Now, the next case is slightly more complicated. And in order to handle that case, we will develop three separate specifications, and then we will use schema calculus to join them together. And these three separate specifications are for the case of destroying the process. Now this process could be destroyed if it was using the CPU and it finished its work and then it doesn't need the CPU anymore, so it is destroyed. This is one possibility. Another possibility is that this process is waiting and we destroy this process, kind of kill this process explicitly. We say kill it. Now this process could be in the ready queue, or process could be in our blocked queue. So we could have a process sitting in the ready set or a process sitting in the blocked set. So if it is destroyed when it was using the CPU, then that was the current process. What will happen in that particular case is that, current will become null, nothing else will change. and the PID that was assigned to this process has to be returned back to the free set. In the case of when the process is in the ready queue or the ready set or the blocked set, we will remove this process from those sets and the ID will be given back to the free set so that it could be assigned to some new process that comes. So these are the three different scenarios that we have, and for these three different scenarios we are going to write three schemas and then join these schemas using schema calculus. So let us look at the specifications. So we have this a destroy current, which destroys the current process, changes the scheduler, and in this particular case we say that the PID that we want to destroy is equal to the current, and then current becomes null, nothing else changes, and so ready remains ready, blocked remain blocked, the same thing, but we add the PID of this current process to the free set. If we destroy a process in the ready set, in this particular case this P has to be a member of the ready set. Then the only two things that change that are the ready set, so this process has been taken out from the ready set, and the free, in which we have given this process ID back to the free set. And if we destroy a blocked process, once again the precondition is that this process is a member of blocked, and if that is the case, then current does not change, ready does not change, the process is taken out from the blocked set and blocked set is updated and free set is updated accordingly. And our destroy schema is, we get a new schema by combining all three schemas. So we have the first one or the second one or the third one. So we have a destroy current or a destroy ready or a destroy blocked, and that gives us the destroy schema for the destroy. So here once again, although there is nothing new, but the point once again is small specifications. We identified three different cases. So instead of writing specification that would take care of all these three cases at one place, we defined schemas to handle these three cases separately and then joined them together. So this is a very convenient way of writing specifications, because we can separately discuss and design those specifications. That makes it simpler and easier to understand, and then we join them together using schema calculus. Now let us move forward and then apply some refinement to these specifications. Note one thing here, that as far as the destroy or create is concerned, we are simply adding one new process to the system and destroying one process from the system. This destroy is complete. There is very little room for a sort of undeterministic behavior. We are destroying one element and we are putting that ID back into the free set. But in all other, starting from add and dispatch and so on and so forth, the question is, when we add, where do we add? We simply put it in the set. When we dispatch, which process do we take? When we add, which process ID do we take out from the free set? When we dispatch, which process do we take from the ready set and give it the CPU? And so on and so forth. So this non-determinism, it is good as far as the specification is concerned, because it tells us what needs to be done at a very high level of abstraction. But from the implementation point of view, there is non-determinism. If we wanted to write a compiler, we would have problems because we would not really know, what would be the policy. So when we introduce policies, that means we take certain flexibility out. And this is what we are going to do, and this is what we shall see in the subsequent phases. So we have now the design. The first step that we are going to take is that our program will use a simple data structure, an array, and a few counters. So we have decided to use an array to implement our sets. Our use of this data structure can be modeled using chains, which is an infinite injunction from PID to PID, and will have a unique start and a unique end. Now we are talking about designing. The first thing is that we have made this decision that we will be using arrays. Okay. And the second thing is that, the different data structures, for example, the ready, the blocked, these data structures, they will be implemented, or they will, use the concept of a chain. Chain, as I mentioned, is going to be an injunction from PID to PID. So that means if I am at one point and this chain, I follow the chain, it takes me to the second point, which gives me a PID. So I am at a PID, I am at a point, I am in my chain, and that particular node or entity is identified by a PID, and I say forward, it follows the chain, follows the link, takes me to the next element, and so on and so forth. So actually what I'm talking about here is, without explicitly saying, I'm having a linked list. I am having a chain, and I will be following the elements in the chain. So this is the concept of the chain, that is, I have this linked list. Now I will be using these data structures for my refinement of the original schemas. So let me take you back to the slide and show you what we can get. So first thing is that we define a chain. A chain is defined to be set of all PIDs that appear in the chain. So we have a start and end of a chain. Remember that we said that a chain will have a unique start and unique end. There are going to be links which will take me from one PID to another PID. And we have a finite set of PIDs, which is set of all PIDs. This set is set of all the PIDs that will appear in this chain. The elements of the chain will be connected, and every one of these may be reached from start by applying the function that links a finite function links a finite number of times. So what we have here is, we have now the predicates. So before I talk about the predicates, just let me elaborate this thing once again. We have the notion of kind of a linked list. We have a unique start and a unique end. And every element in the list, in this chain, can be reached from start. So if you start from here, there is this function links that we have in this particular specification. This operation links takes me from one node to the other, and these nodes, they have PIDs in them. So the start will have a PID, and I apply this links operation on it, it will take me to the next one. Then it will take me to the next one. When I apply it there, it will take me to the next one, and so on and so forth. So it is a simple kind of an operation that I want to define, that I would have on a kind of a linked list, जो हमारे मशहूर famous से operations होते हैं. So let us now go back to the predicates and look at the specification of chains. So this, in the chain, the set is equal to domain of links union range of links union start minus null PID. This set is the set of all the links, all the PIDs that are present in this set, in this chain. And what we are defining is, we have the domain. In the domain, we are, for example, each node, we apply this links and we go to the next one. So we have all these domains that will take me to the next one. So all the domains, including the start one, is there. All the elements in the domain of this links is there. The last element in this chain is my end of the chain. Now, this last element is not part of the domain because I cannot apply links onto the last element, and it does not take me to the next element because there is nothing after that. So that means, I have all the elements in the domain, plus I have all the elements in the range. So that will take care of all the elements that I have in the chain. And plus, I have the starting element. So all this is what I have in my set. Now, this links is equal to empty set, or links is equal to null. That implies start is equal to end. So in this particular case, what we are saying is that, when we have this links equal to phi, null, that is, the map is not defined. That means we have nothing in our chain, and the only thing is start and end, and both of these, they collapse onto one element, and that is what we have. So for every chain, even if it is even if it is an empty chain, we have start and end. Those are uniquely defined. In this particular case, they would be collapsed onto one. So this is what we have when we have nothing in that chain. When the chain is not empty, that is, links is not equal to phi, that implies that start is equal to domain of links minus range of links. Domain of links and range of links. When it is empty, domain of links and range of links is not defined, because you start from here, but you cannot go anywhere else. But range has one additional element, that is your end. Domain does not have that. So if you delete everything from the domain, what you get back is just the start one. So you take whatever was there in the range. The start is not present in the range. The end is not present in the domain. So if you take the domain and you take the range, you subtract the elements that are present in the range from the elements that are present in the domain, what you are left with is just start. That this is set subtraction. So remove all the elements that are present on the second set and get whatever you have. And in this particular case, you will get only one element, and that will be the start element. And end is equal to range of lengths minus domain of lengths. Just the opposite. Now, in the range of lengths, you have the last element. In the domain of lengths, you have the first element, which is otherwise not present. So you subtract that from there, and you get only one element, and that will be the last element. This is the case when lengths are not empty. And finally, we say for every E which belongs to this set, when E is not equal to start, start is mapped onto E is a member of lengths plus. What we are saying is this E is a member of the set of all the PIDs in the chain. And what we are saying is that this E can be reached from start by applying this links a number of times. So, that means every element in the chain can be reached from start by subsequent application of this link. And ultimately, you will get to that element if that element is present in that set. Now, the question is, how do we know that the start and the end of a given chain are uniquely defined? And the second question is, what must be true of the start and the end PIDs if set is empty? Now, we consider these two questions. When set is empty, that implies start is equal to null PID and end is equal to null PID. With this above invariant, when the set is empty, there is nothing there. Initialization of the chain is, we have this chain in it. We say start, the new value of start is equal to null PID and end is equal to null PID. So what we are saying here is that what do we have at the beginning? At the beginning, the set is empty. When the set is empty, so what is the value of start and end? Remember, when there was nothing in the lengths, we said this start and end would collapse, they would be equal. So what is that value? In that particular case, both of these, they are equal to null PIDs. This is what we have said. So this chain is, in order to initialize that chain, we will apply this property. That is, initialize means that the set is going to be empty, and hence the start and end both will be assigned this value, or both will be equal to null PIDs. Now we apply some more operations on the chain. So we have push, which pushes an element onto the end of the chain, pop, which pops an element from the front of the chain, and delete, which deletes an element from the chain. So when we have an empty chain, that is, we are pushing the first element onto the chain, we write the schema push empty, which changes the chain, and in this particular case, end will be equal to null PID. This is the precondition. This is the empty chain. So end in this particular case will be equal to P, and links will be equal to this links. And when we push onto a non-empty chain, in that particular case, end is not equal to null PID, and links will be equal to links union end mapped onto this new PID. And push in this particular case is push empty or push non-empty, and we are using the schema calculus for that. Similarly, we have this pop singleton. In this particular case, we are saying that we have only one element in the chain and we are popping. So start in this particular case is not equal to null PID. This is the precondition. Links is equal to empty because there is only one element, so there is no link. Start will be equal to null PID. Links will be equal to links. It will remain empty, and the element that we return back is equal to start. And when we have multiple elements, in that particular case, links are not going to be empty. We have links that define this thing. Start will be equal to links start, and links will be equal to this, taken this start out of the links, and you have the remaining links. And then we have this P of start, which is output, and once again we use schema calculus to define this pop operation by joining this pop singleton a pop multiple. Here what we have done is we have created two operations on this schema, on this chain, which is our data structure. One was push and one was pop. In the case of push, there were two cases, two scenarios. One is when we were adding the first element to the chain. Chain was initially empty. When we add first element to the chain, that first element is the same as the last element. There is nothing. You cannot, you go to the start, you cannot follow the chain. There is nothing in the links. So links are empty in that particular case. Start and end, they are the same. This is the first case. And when it is not empty, what you do is you add one element to the end, you update the end, and you add one more link and add this end to the domain of your chain, of your links. Just adding one more element to your chain. Similarly, pop has two cases. One is that there is only one element. When there is one element, that means after popping that element, you will get the empty list, the initial condition. When there is only one element, that means, start and end, they are the same, and there is nothing in the links. You cannot have the next element. There is nothing. There is only one element. So this relation links doesn't have anything. In that particular case, you will, simply take that element and update your data structure accordingly. And if you have more than one element, that means this links is not going to be empty. So in that particular case, you're taking the first element from the chain out. So what you do is you're reducing the domain of links by taking the start out and then assigning this new start, which will be the first element in the link, in the chain. And that's how you do that. So what we will do is we have used this basic data structure. We have defined this basic data structure, which is chain. We will be using this data structure to implement the scheduler. We will be doing that in our next lecture. Till that time, Khuda Hafiz or Assalamu Alaikum.